Hello, this is Jonas from vhdelvis.com. In this video I'm going to take a deeper dive into this week's blog post, and I'm going to link to this blog post in the video description so that you can download the code that I'm working with and you can run the examples on your own computer in ModelSim and in Lattice IceCube 2. And the blog post that I'm talking about is this one: how to create a breathing LED effect using a sine wave stored in block RAM. That's right, I'm showing you how to create a sine wave by using VHDL, and then how to store this sine wave in block RAM in the FPGA. And also we are using this as a demo for creating a breathing LED effect on the power on LED on the Lattice iStick FPGA development board. So click the video description to get to this blog post. But I should say that this article, this tutorial, it builds on the article from last week and the video from last week. So last week we created a PWM controller, that's pulse width modulation, and that's a way of controlling an analog device from a digital FPGA pin simply by switching on and off the FPGA pin and switching on and off the supply current that runs through the device with a fast rate. So then we are able to control an analog device or the power flowing through the device in an average time window very accurately. And that's what we created last week, and we controlled the LED on the iStick with this pattern, this duty cycle of a sawtooth pattern. When the duty cycle is 0, then the LED is off. When the duty cycle is at the max value, then the LED has the max brightness, and anything in between is just a linear value between the max and the min value. And in the new blog post for this week, we are controlling the duty cycle by using this sine wave. So we are creating an LED breathing effect, and by breathing effect I mean this continuously on and off, which looks very natural because there are no abrupt changes in the light illumination or the illumination intensity. And we're going to create this now in the Lattice iStick FPGA, and everything that I'm doing now is in the article, so I'm not going to go in details here because all the formulas are here, all the code is here. And if you want to download the code, if you want to download the examples for ModelSim or for the IceCube 2 software and run it on your own iStick if you have one, then you can use this form in the blog post. So just go to the video description and go to the blog post and download the form. It's very easy to use it. There's an explanation in the how-to txt file and in this GIF which shows you how to run the example. So just enter your email address and click give me the files. And I have of course already gotten the files, so I'm not going to go through how this module works because I'm going to elaborate on this design in this video. We're not going to explain the code because that's very thoroughly explained in the blog post. So let's first run this design in ModelSim. If you downloaded the example, you can run it by using the run script, and everything is in the readme file, the how to use readme. It says that you should run the script, and I have downloaded it to my computer and in the LED breathing folder, which I downloaded, or you can download. You can run the run.do script by typing do run.do in ModelSim. And I have done just that, and it will print out a usage manual or how to use this in the ModelSim console. Thank you for downloading this example from vhdelvis.com. Type run tb in the ModelSim console to run the test bench like this, run tb. So let's do that. And this script, it works in Windows or Linux. I'm running Windows now, but it works in Linux too. So all my examples, they work in Windows as well as in Linux. So let's see the waveform. The duty cycle has this sine wave pattern, and that's good because everything is working. But let's have a look at the LED output. So this is the one that controls the LED if it's on or off. So at the top of the slope here, we can see that the LED is continuously 1 because that's the max value. Then it starts to get longer and longer periods of being turned off, like at this point it's 0 for perhaps 1/10 of the period. Oops, let's go out again to zoom out. Then let's see in the middle of the slope here, between the min and the max, then it's more like a 50% duty cycle. So the LED is off as long as it is on. And at the bottom of the slope, the output is continuously 0. So that's working nicely. The output here is continuously 0 until the slope of the duty cycle starts rising, until this value starts rising. Now it's 1. Then the output is for a short period of time. There are some spikes that illuminate the LED, and the duration of these spikes continue to rise as the duty cycle rises. So this should be able to control the LED on the iStick board so that it looks like it's this smooth breathing effect. But first, before we implement it on the board, we're going to have a look at the logic that this code creates. So we're going to open IceCube 2, and the project that I'm opening now is the LED breathing project that you could download in the zip file. Inside of here, in the IceCube 2 project folder, there's a project folder which you can use to open the source files. So I have a pre-made project for you, and I have already opened it in IceCube 2, but I haven't run it yet. So I'm going to run it now by going to Tools, Run All, to implement this design and create a bit file so that we can program the FPGA. And we're going to do that in just a few moments. But first, let's see if this works, and we're going to also check out the synthesized netlist, and that's a good practice for FPGA engineers. So the bitstream has been generated, so we are ready to program the FPGA. But first, I'm going to open the synthesized netlist. So to do that, in IceCube 2, you can right-click on this menu item, Run Simplify Pro. Right-click, select Options, and from this menu, there's a small link which says, click here to run Simplify Pro, or to set Simplify Pro options, click here actually. When I do that, Simplify Pro opens, and this is the synthesis tool behind IceCube 2. And we can see already that it's using 1 block RAM. It says here, RAMs 1 block RAM, 1 RAM. And that is the sign ROM. We're going to have a look at this one. Let's open the RTL view. So if I go to the menu here, in RTL view, click this button, then it's going to open the logical components that the synthesizer has created. And let's see if we can recognize something here, because this is the VHDL code that has been synthesized, and this is the interpretation that the synthesizer has created from our code. So let's see in the blog post, for example, we have an overview here. The overview over the top module, which has a reset input, reset module. This is a reset module. And there it is in the synthesized netlist, the reset module. And then there is the counter module, which creates the sawtooth counter. And there we have it. And this next one is the sign ROM. And it is there, downstream from the counter. And after the counter comes the PWM module, which is also the one in our diagram and in our VHDL code. And the output from the PWM module controls the LED. So everything is inside of here, and these are the LEDs that are just turned off. They are continuously 0. But this is the... Oh, actually, no, it's not. This is the LED. One of the LEDs, PWM output, is connected to LED number 5. The others are 0, as I said. I've just connected them so that they are turned off and not illuminating faintly. And this output pin, that's another story. This is for, I'm going to click on this one, which will take me to the code. It's an output pin. It's just a copy of the LED 5 output. So we're going to use this one, this output pin. We're using this one to connect our oscilloscope to. So that's why I have created a copy of this PWM output on a regular pin on the iStick board. And we used this one in the previous video for the PWM module. We used it to connect our oscilloscope to, and we're going to do that now in this video too. Now what I want to do is to look inside of these modules and see if I can make sense of the code, because that's a good practice to do when we are designing VHDL. And inside of the reset module, for example, here we can see a shift register which takes in the negative reset from the pin, because this negative reset is connected to a pull-up. I wrote that in the comments here. It's connected to a pull-up. This is the entity for the reset input on the top module. And because of that, this shift register is going to fill up with 1 values. It's 0 initially when the FPGA starts. Then it's going to fill up with 1 values. And when all of the values are 1, then this AND gate is going to output 1, because that's what we are describing in this process right here. If I click on this one, it's going to take me to this process where I'm describing this behavior. So if shift register is all ones, so all ones here, this is a constant, then output 0, if not output 1. So it's actually the opposite behavior. So if all ones, output 0, that's an AND gate. If not, output 1. And that's realized by the synthesis tool by this AND gate and an inverter. You see that? And out comes the positive reset, which goes from the reset module. That makes sense to me anyway. And next downstream is the counter module. So this one is just a counter. Let's double click this one to go into the counter module. And here we have an adder and a flip-flop and some inputs and outputs. And the count enable input, this one is actually unconnected. In our code it is unconnected, or it is connected to a constant 1. Here, constant 1. See that? The counter module is connected to, or the count enable input on the counter module is connected to a constant 1. And we can find this in our code as well. If I go to the top module, you can see there, zoom in on this one, you see that? Constant 1. It's not connected to a signal, it's just a constant 1 value. Okay, back to the counter module. So we have the clock input that goes to the flip-flop, and the reset goes to the flip-flop. This one coming from the reset module that we just talked about. And the output is the counter value, because we're using this one in the rest of the design. But what happens in this feedback path? Well, let's start by looking at the initial values when everything is 0, because this flip-flop is actually 25 flip-flops, so it's 24 down to 0. This is an array of flip-flops, because if we click this one, we can see in the code. I'm not sure where it went, but it's this one based on the counter range. And if we trace this back in our VHDL code, it's going to go to the entity here, the length of this counter length signal, and the counter length signal. The counter signal, this counter, is based on the count bits generic input, which is 25. So we are creating the counter with 25 bits length, and we can see this replicated in the code here with a 25 bits or 25 flip-flops. So what happens when everything is 0? Well, all of the flip-flops are storing 0 values, and this output is 0. Then what comes out here is going to be 1, because this is an adder adding this 25-bit value to a 1-bit value, and this one is constantly 1, as we know. So the output from this adder is going to be 1. And this counter or adder, this is a combinational primitive, so it doesn't wait like the flip-flop. It just outputs immediately this one plus that one, and the output is right here. And it goes back to the flip-flop, and on the next rising edge of the clock, this value is going to appear there. And it goes through, of course, the same value. The next value, it goes through the counter, and immediately the one higher value is going to appear here on the data input on the flip-flop. But because the flip-flop is an edged triggered device, the output won't change until the next rising edge, and that's how our counter module is working. And the output from the counter goes into the sine ROM. Actually, it's not a complete counter, because here you see the full counter 24 down to 0 comes from the counter module, but only 24 down to 17 enters the sine ROM and the address input on the sine ROM. And why is that? That's because in our code, in the top module, the address input, the one entering the sine ROM, this address input, this is an alias. This is an alias which picks out the high bits of the counter signal. So it's based on the PWM bits input, which is 8 bits here. So this is the resolution of our sine ROM counter, or our sine ROM. So we are using the max, or the most significant bits of the sawtooth counter to address our ROM. That's what we're seeing here. The 8 highest bits from the counter are being used for the address input on the ROM. And if I click into the ROM here, we can see what we have here. Actually, we have the address input and the ROM. You can see it says ROM here. So the synthesis tool has created a ROM out of this. Then it goes to the output from the ROM goes to a flip-flop, which then clocks the data out from the ROM. Because in the lattice FPGA, this ROM seems to be treated like a combinational component, because actually this flip-flop is it is going to be inside of the ROM. It has to be inside of the ROM because the block RAM is an edge triggered device. We have to have the clock signal on this one. You see here, this is the code for the ROM. On the rising edge, we are clocking out the data from the address, or based on the address from the ROM, just like that. And then the code, or the output from the ROM, which is now the sine value, or the sine wave, goes into the duty cycle, and this is the value here. This one goes into the duty cycle input on the PWM, is going to produce this PWM output, which goes to the LED. So if we click into this PWM module, it's a bit more complex, and I don't think we have time to go through this one. But what I want to do is to go look at the technology view, because this is the RTL view. It's the register transfer level view, but I want to see the actual devices that are being used. So besides the RTL view here, we can click on technology view in Simplify Pro. It's going to show us the exact primitives that that are going to be used on the IceCube 2, or the ICE40 device. The FPGA is called an ICE40 device. And this is a bit more it's difficult to make sense of, because there's going to be a lot of different components. So I usually don't go into this technology view, because quite frankly, when the device or the project gets more complicated, it's going to be impossible to make sense of. But we can look at the sine ROM, because let's see what kind of primitive it's going to use there. So if I click into this sine ROM of ours, we're going to see that the synthesis tool used a specific RAM primitive, the 256 times 16 RAM. So 256 deep, 16 bits wide on the address input, but we're only using 8 of these 16 bits. So that means that we were successful in using this or mapping sign values to a ROM. Okay, so we can see here the outputs from the ROM. It is the high bits are not being used, only the low bits, because that's how ROM or block RAM works in FPGAs. If you're using some parts of the ROM, then the whole ROM gets wasted, or you can't use it for anything else. And it goes out the duty cycle, the data output from the ROM. And I can also right click here on the ROM and select properties. We can get even more information from this, and even the initial values. So this is the values that comes from our function here, the function that initializes the ROM, the init ROM function in the signrom.vsj file. These are the values that are actually being created. And we're not going to go into the details of this, but it's a good exercise to at least watch or check out the RTL view. And you should always check out look at the you should always look at the resource usage, and if there are any warnings like synthesis warnings, you should always look at them. And that's what we do in the advanced dot matrix course. So if you have been following VHDLWiz, you know that I have an advanced course as well, which is called dot matrix, and it's going to open for enrollment the 8th of June next time. And if you want to learn VHDL and FPGA design on a higher level, how to create self-checking test benches on every level of your design hierarchy, how to inspect synthesis logs, and how to inspect RTL schematics after synthesis and relate it to your VHDL code, then that might be something for you. So it's something to look out for, the dot matrix course that I'm going to launch or open for enrollment the 8th of June. Okay, enough about that. Let's go back to IceCube 2 now. And we have already synthesized and routed the design. We did that before we opened Simplify Pro. So I'm going to go into Diamond Programmer, and I have now connected the ICE40 or the iStick FPGA board. So I'm going to program with our bit file. I'm going to program the bit stream onto the FPGA and see how it looks. So we're programming, the LEDs are flashing, and there we go. The design got programmed. Let me see here. Programming failed. It did not get programmed. So let me see here. Perhaps I was wrong. We have to synthesize once more. The binary files probably got deleted somehow. I'm not sure. Let's just go through it again. And there we have it. Let's press the program once again. And there we go. Operation successful. So here is the iStick. We can see the LED is breathing, I can say. It's illuminating, and the brightness goes between off and completely on, but with a nice sine wave pattern. So it looks very natural. Let's connect the oscilloscope and see if we can make any sense of the output, the PWM output. So I've connected the oscilloscope and I'm turning it on, and there we can see the duty cycle replicated on the PWM output. As the output gets as the duty cycle gets to the max value, the active period on the PWM output gets longer. But it's going a bit fast now, so I can't really spot or see what happens at the high value and the low value. So what I want to do is to go into the code now, and I'm going to make this a bit slower by increasing the number of count bits. So if I increase, for example, from 25 to 29, then this is going to make the oscillation is going to be 16 times slower, because I increased by 4 bit and 2 to the power of 4 is 16. So let's save this now, go to IceCube 2 and Tools, run all, to program or to generate the bit file once more, because I want to observe what happens when we get to the top of the slope, when we get to this point, to see if actually the output is continuously 1, and when we get to the bottom of the slope, to see if it is completely off, because these are common errors for PWM, to not turn completely off and not turn completely on the top and the bottom. So let's see if we can program the FPGA. Now the new bit file has been generated, and I'm going to program the FPGA. And there we see it's going a lot slower now. And what happens when we approach or get to the max value? There, you see that? It was continuously 1, it was continuously high for some time. And then when we get to the bottom of the slope now, is it going to turn off completely, or will there be small spikes indicating an error? There we go, completely off and back again. So that looks very good, and that's actually all that I'm going to do in this video. You know, the next video is going to be about making this work on Linux, because right now I have been marketing my courses for Windows because I haven't had any way to run the software, the free software on Linux. But I have already created a blog post about how you can get ModelSim working on Linux, the free version that comes with the Intel Quartus Prime edition for Linux. I have created a blog post for how you can get it working on Ubuntu Linux. And the next video that I'm going to create is going to be about how you can get this Lattice IceCube to work on Ubuntu Linux. So that's going to be next week. But that's all for this video. So I hope you enjoyed this, and if you have any comments, please leave them in the comment section for this video. And that's all for now. Talk to you later.